Let us look through some examples of differentiation. As you will see later when we come to integration, differentiating functions is not that hard compared to integration. That's because no matter what complicated function you are given, by repeated application of the various laws of differentiation, like sum of derivatives is derivatives of the sum, then product rule, Leibniz product rule, and chain rule, you will be able to differentiate any complicated function provided you have the patience. So let's see first example. Well, the first example is the derivative of constant function is, as you can expect, 0. This is because the numerator in the Newton quotient will be identically 0. That's fairly easy. And next, if you take f of x equal to x on the interval I, then f prime x is just identically 1. Okay, why is this? Well, because at a given point to take the derivative, you will have to take x plus h minus x by h going to 0. This will just turn out to be 1. So because the Newton quotient will be identically 1, the limit will always be 1, and the derivative of the function f of x equal to x, that is the identity function, is, as you can expect, constant 1. Okay, third example, if you take f of x equal to x power n, well, there are several ways to prove find out what the derivative is. My favorite way is to just repeatedly use the fact that if you take x squared, let's for instance take x squared, then let's call this g of x, then g prime of x is clearly 2x. This is just by Leibniz product rule, Leibniz rule. And how does this generalize to x power n? Just apply induction. Just apply induction now. That is, assume that derivative of x power n, if you take x power n, let's call this h of x, then h prime of x is nx power n minus 1. Then if you want to differentiate x power n plus 1, just apply this Leibniz product rule. This is just x into x power n plus 1. Now when you take derivatives, you just get, x into x power n. So when you take derivatives, you just get x power n plus x into nx power n minus 1, which will just give you x power n plus nx power n, which is n plus 1 x power n, which is what you want. There is another way to do it by using an algebraic identity. I leave it to you in the exercises. Okay, so far 3 simple examples. Let's slightly modify this example, at least in the case. Take mod x. This function, as we all know, is continuous. This function is certainly continuous. And this function is equal to minus x if x is less than 0. And x if x is greater than 0. Again, in fact, greater than or equal to 0. So the derivative of this function, is minus 1 if x is less than 0 and plus 1 if x is greater than 0. This much we know. What about at x equal to 0? Well, let's check what happens. You have to take mod of x plus h minus mod x by h. And here x is just 0. So you just have to take mod h by h. This is the result of the Newton quotient. If h is less than 0, then Newton quotient is minus 1. If h is greater than 0, then Newton quotient is plus 1. Limit as h approaches 0 does not exist. So this function is not differentiable at the point x equal to 0, which is sort of intuitive because the picture of this function looks like a v. Okay, now the interpretation is that the slope of the tangent at this particular point doesn't make any sense. There's a sharp bend. This curve, the graph is not turning smoothly at the point 0. It seems like an abrupt break. So you are not able to define the slope of the tangent at that particular point. Okay, so the derivative here is not defined at x equal to 0. Okay, let's take a more complicated example where things start to go wrong at the origin. Recall the function sine 1 by x. Recall the function sine 1 by x. This is the function that I dread drawing every time because it's insanely difficult to draw. It just oscillates wildly as you approach the origin. However, even though it oscillates wildly, it oscillates between +1 and -1. That's a basic property of the sine function. So let's try to temper these oscillations by multiplying by x. So consider the function f of x that is defined to be x sine 1 by x if x is not 0 and 0 if x is equal to 0. We already know that this f is continuous. This we have seen in the example section of continuity. Now, let's try to take the derivative at the origin. So what you have to do is take h sine 1 by h minus 0 divided by h. This just gives sine 1 by h, and therefore this function is not differentiable. F of x is not differentiable at 0. At 0, because you end up with the function sine 1 by h, which is not defined when as h goes to 0. This wildly oscillates, the limit does not exist. So f of x is not differentiable at 0. Okay, so tempering with x did not help. Well, let's temper with x squared. Maybe that has a better effect to temper down the wild oscillations of sine 1 by x. Remember, as x approaches 0, x squared sort of goes to 0 faster than x. So that's the idea. Maybe this will help. Well, again, we have to take, so again, let me define the function. F of x is x squared, sine 1 by x if x is not 0, 0 if x is equal to 0. So let's take the Newton quotient. So it will be h squared sine 1 by h minus 0 by h, which is h sine 1 by h. And this approaches 0 as h goes to 0. Because the oscillations of sine 1 by h are bounded between plus and minus 1, and the factor h will ensure that the product is 0. So the function x squared sine 1 by x is indeed differentiable at 0. Okay, and the derivative is 0. Okay, now let's try to figure out what the derivative's behavior is. We already know that f prime of x is 0 if x is 0. What about other points? Well, we can use the product rule, chain rule, and so on. So x squared sine 1 by x, when you differentiate, you will get 2x sine 1 by x plus x squared times the derivative of sine 1 by x, which is cos 1 by x, times the derivative of 1 by x, which is minus 1 by x squared. Okay, this just comes from the quotient rule. So what you get is cos 1 by x plus 2x sine 1 by x. Okay, now let's take limit x going to 0 of this. Okay, or rather let me write it better. As x goes to 0, the second term vanishes. Okay, however, cos 1 by x wildly oscillates. Which means this function, the derivative f prime of x, is not continuous at 0. Is not continuous at 0. So conclusion is the derivative of a differentiable function need not be continuous. There could be discontinuities of differentiable functions. The next natural question to ask is how do the points of discontinuity of the derivative look like? This is the next question that should be on your mind. Here in this case, we got this function cos 1 by x as one of the terms in the derivative, and that oscillates wildly. So the singularity, or rather the point of discontinuity at the origin, is very badly behaved. There is a wild oscillation. The simpler form of discontinuities that we have studied, jump discontinuity, is not occurring here. Okay, so I'm going to leave you with an exercise. Explore. This is an exploratory exercise, so it's up to you how much time you want to spend on this. You can spend the next 10 years doing a PhD on this, or you can spend the next maybe an hour or so. It's up to you to how much you want to explore. Explore f of x sine 1 by x for various functions f of x. So one recommendation is f of x equal to x power n. We have already seen x and x squared, higher powers. What happens? And can you temper sine 1 by x in different ways? How can you adjust the behavior at the origin by multiplying by various other functions f of x and see what happens? Okay. So we have now seen some examples of differentiation, and we have also seen that the derivative does not always behave nicely. Even when you temper it appropriately, the sine 1 by x function, there seems to be some problem with the derivative. Now, in a later module, I will show Darboux's theorem, which says that the derivative will nevertheless satisfy the intermediate value property. Now, why is this important? If the derivative satisfies the intermediate value property, then it cannot have jump discontinuities. The derivative can only have such wild oscillatory discontinuities, cannot have jump discontinuities, and that's for a later day. This is a course on real analysis, and you have just watched the module on examples of differentiation.